Hello, Tom Marsh again with the assignment part of the Astronomy at High Speed. So make sure you watch the Astronomy at High Speed presentation first before you go on to this part. The assignment is all to do with binary stars that are talked about in the presentation, but it's best to start off with that part. The assignment, as with the other assignments, is all done through IPython notebook, Jupyter notebook, which has a series of sections, text, and runnable parts with code in them. I'm not going to try to go through all of this, and I'll appreciate that the font I'm going to be using here is going to be quite small for this video, so I'll just have to, hand it over to you to read it in detail. Okay, so let me start off. So this is what the Astronomy at High Speed notebook starts like. Okay, you've got a few controlling parts at the top here, and this, by the way, is after you should see this after you've downloaded the files from GitHub. I'm assuming, and you run notebook in the correct folder. And then it has a series of sections which are sometimes just pure text, like this top one here, and other parts which are going to be code. So if I go a bit further down here, it's got a code section. So if you have any problems, please contact me on Slack, the ThaiPASS, I should say 2022, I'm sorry, Slack workspace. Please contact me, and I'll be very happy to try to help out. Just an indication, if you've got the right files, they should be names like binary.py and have some data files, data01.txt, and you should also have this notebook which is called Astronomy at High Speed.ipynb. Okay, right, so the intro section here, please read it. I mean, I appreciate it's not English, not your first language, so it's going to be difficult maybe, but I hope someone can help you out with some of the technical terms. It's to do with eclipsing binary stars, and there are quite a lot of details, such as what do I mean by orbital period, what do I mean by the orbital inclination. So try to get a good understanding of each of these terms here. I make some simple approximations. I'm going to assume circular orbits. I'm going to be talking always about totally eclipsing systems, and that tells you a bit more about that. Okay, so then the first binary section, I've got my mouse here, and if I click on it, I highlight it, and then I can run it. Okay, and when I run it, this one is designed to create a sort of artificial binary, and in an animation. So I hope to show that. You can look at the details of the code if you want. They're not too bad, but they will take a bit of getting used to if it's your first time. Not a very long bit of code, mostly comments. So here I'm going to run it. Okay, so this is an animation where we have the view of the binary as seen from Earth, where we don't see any three-dimensional information. We just see the stars projected onto the sky, and so this idea of the plane of the sky, where you're just seeing everything pasted onto it like a painting, like a two-dimensional picture, is an important part. And this is what it looks like to us if we could zoom in onto the star. And so these two stars are completing a circular orbit. It's not completely edge on, so they do move. It's slightly tilted. If it was edge on, that would be 90 degrees, but it's 87 degrees. So they're very edge on, so that they do eclipse each other. And you notice red is in this case meaning a cool star, it's the large one, and blue is meaning hot. This is an astronomy way round, which might seem a bit odd, but that's the way round we have it. The red star is such that it will completely obscure the blue star, which I just show slightly. You can just see it just in the background there, but you should really imagine it's completely obscured. And when it passes it's behind the red star, then you don't see any of its light anymore, and so we'll end up getting this eclipse. So here we are, we're going along, so the red star is about to start coming in front of that blue star again, and we'll start coming in around here. So there we go, down, up, and that's just when that's being obscured. You can slow this animation down if you want, by the way. If you look at the code, it's very easy. Here's the other way. This is when the blue star goes in front of the red star. It doesn't. This is dimmer on average per square degree, and so it's a smaller effect. Okay, so when you want to still kill that, you just click X there, and then we're on to the next section where we've just got a still from that movie. And there are a few exercises therefore associated with this. So for example, exercise 1 here, on the plane of the sky the maximum separation between the centers of the two stars equals 1. Okay, that's from here to here, 1. Shows that the minimum separation is given by the cosine of the orbital inclination. So you'll need to understand the definitions that we had before. Have a think about that. If you can't get anywhere with it, there is a hint available, and I just quickly whiz down to the bottom here. So here are some hints. I'm not going to look at those now. Try to answer it without the hints, but I hope these might help you out if you're stuck. They're not very easy. But, you know, if it's the first time you've seen this sort of thing, these are quite difficult. You need to visualize. So think a little bit. These are pen and paper exercises at this point, but I want you to write them up in the form of a notebook for your answer. So write them up into a notebook like this. When you do that, a very useful feature of these notebooks, you see it's nicely presented here, but if I highlight that and if I double click, you can see how it's actually written up. This is how you actually type it when you're trying to type up your own notebook. Okay, so you'll be able to learn some tricks just by doing that. If I go back and run it again, I go back to the nicely formatted part. Okay, so that was that section, and those are the associated exercises, and I'll leave you to read those. Okay, and then it goes on a little bit more and talks about what we call contact phases and fluxes. Okay, so this is a way in which we define particular points within the orbit in order to solve for interesting parameters. So we're not so interested in the particular times at which things happen in the light curve as things like the radius of the binaries, the radius of the two stars, but we can deduce those from the shapes in the light curve. So for example, if I go down here, if we look at an eclipse like this, we have a particular phase here when we start to first eclipse the blue star. This is the phase at which we fully eclipse the blue star, and we call those contact phases, and this is the same thing. So this is what it would look like on the sky just at the point we're starting to eclipse the blue star, and this is what it looks like on the sky just when we finished eclipsing the blue star. So from this point onwards until we get to this sort of configuration, all we see is the cool star, and so there's no change of flux. So that corresponds to going from here to here and then having this flat section here at the bottom. So a flat bottomed eclipse is a very common, is a useful way to see a totally eclipsing system like this. Okay, so you can use measurements of where that phase is and that phase is, and some other details explained here to deduce important parameters of the binary, the radius, how inclined it is. These are the key features when we're trying to solve a binary. So I'll leave you again to look at that, because that's all fixed stuff. And then there are some associated exercises here. Again, these are pen and paper exercises, but I want the answers in a notebook form. There are another couple of hints available down at the bottom again to help you out here. I hope you find these exercises interesting and just trying to conceptualize these sort of binaries. Remember, everything's spherical and they're on circular orbits. Right? Okay, now finally, I have some exercises more Python based where we're trying to see how you make measurements and how those measurements lead to the parameters of interest. Okay, so it starts off with another simulated light curve, and we're going to look at that. So if I click on this, and I'm going to run it, and we'll get an artificial data set that it's going to create, which we can interact with a bit. Let me go there. I'm going to make that a bit bigger. Okay, so this is it's a useful. This is what's called a matplotlib interactive plot, and you can see some controls here. They may appear in a different place for you according to your computer. Okay, but nevertheless they should be there, and they allow you to actually interact with this plot. So, just give you an example. Zoom to rectangle. If I go here, I can zoom in and look in a bit more detail. So in this case, this shows the model, and I've then artificially created data from that model. Okay, so it's a way. What I can do is essentially simulate a binary and simulate the observing process in this way. I can go back, or I could look in a bit more detail here. So you can sort of see these contact phases, and in fact you can see that the contact phases aren't necessarily that easy to measure from real data. So the model is quite clear, it ends here, but so that's the second contact. But if you're trying to say where it was from the data, well, you could probably get it roughly right, but it's difficult. So that's an important part of making measurements. That you can't do them exactly because of noise which has been added. Okay, so I'm going to close that. Go back to here, and then following on from that, we're then going to actually measure some contact phases and fluxes. So in the previous section it saves the data to a particular test set of data, and then this next section here will actually go through some measurements. Okay, so let me just run that. It's only a very short section, so run. Okay, what it actually shows up is it shows up a figure you won't be able to see at the moment, but just to go down right, so you can see around here, sorry, it says left click to define the horizontal location of the third contact. So in this case I'm actually going to be making some measurements of these values. Okay, and just to show you what I mean by that, go over here. Okay, here is the image, and if I zoom in here a bit to make it a bit easier for myself. Okay, so sorry, let's go out again. So remember, I'm looking for the third contact. Right, first contact, second contact, third contact, fourth contact. It wants me to define the third contact, and I would say, well, it's obviously not. That's not there. That's not there. It's going to be around here. So I move my mouse there, and then which you won't be able to. Sorry. I made it too large. Let's do that again. So I say first, second, third, fourth contact here, and I'm trying to define the third contact point, which it's not there. It's somewhere in between. I would say it's around here. I move my mouse there and I click, and you won't be able to see what happened there, but it's then, I'll show you it soon. It's now asking me to locate the fourth contact, which I'd say is around here. Then it's asking me to locate the level of the outer eclipse flux, which I'd say is about this, and then the mid primary eclipse flux, which is roughly here, and then let me zoom out again, and then then it wants me to locate the mid secondary eclipse flux, which is about here. Okay, that then I now go back to the text it's been putting up on the screen for me. Here it's gone through. It said left click to define the third contact, left click for the fourth contact, out of eclipse flux, mid primary eclipse flux, and not only so, it's actually recorded all these values, all these numbers here have been recorded. Okay, so I've effectively made a measurement, and then that puts me onto the next text bit, and so we've done all the 5 measurements, and now part of the exercise before is to show that you can actually then solve for the whole system, and this is what this actually does here. In the next cell is now going to use those measurements to work out the radius and how inclined the system is, the key parameters. And so all I need to do here is click run. Okay, and here are the results from that. So these are the numbers that I actually just measured, and then these are the parameters for the binary it deduces, it calculates those. So if you just remember this one here, 86.8 and 0.147 here from the radius, if we go back up, we can see what they were to start off with. They were 87 and 0.15. So what we've done is we've created an artificial binary, artificial data from it, and we've then measured that data and then reversed the whole process to work out what the original binary was. But of course in reality you wouldn't know what they were, but you can still go through the process to measure things to deduce the parameters of the binary, and that's what is done for a lot of binaries. Okay, so at this point you should look at your results and check things are going, and then finally the exercise C, to finish off the 2 exercises here, I've given a set of data files where I haven't told you what the binary parameters are, and your job is going to be to try to use the same measurements, just running this part again here, but changing the file name to match these on here, data 1, data 2, etc. And we're going to then try to work out what the hidden parameters are, which I know but you don't. Okay, so it's a test of whether we can get what I originally put in. So there are different sorts of binaries in each case, and that will be the full exercise. Okay, so I hope you enjoy it. It might take I hope it doesn't take too long, but I hope you enjoy it and try to understand what's going on in the whole process. That's the important thing. You can go a bit further if you want. This is not part of the exercise, but this part here is to show that there are better ways of doing this. This is rather the way that I measured is a little bit tedious, but you can do a little bit better than that. You can actually make the computer do it automatically. So if I run this section here, what it's going to do is to load the text file. It's going to start off with a not a very good guess, because remember it's really 87.15, etc. But it will then gradually try and work out what the parameters are. So let's have a look at that. This takes a lot of computation, so it's quite slow. And you see down here where it says solution, you'll see it starting to add new lines to that. It takes a little while. There we are, so first one. So start off 89.2, 0.3, and then it's gone to 87.15 almost, 0.2. It's already got very close in the very first thing, but it's still changing a little bit, still finding a better model. And at the end of this we're going to plot out a model that will look a bit a little bit better than the well, quite a lot better actually than the starting off model. To be slightly tricky when it does this for me to actually show you the plot that it produces. Okay. So let me Okay, so there is the final plot it's produced, and what that is showing there is sorry, I'm going a little bit too, making that a bit too large, so go back a bit. It's showing the red line shows the initial guess, very bad. Okay, that's the initial guess model, and then there's a blue line that shows the final model that it's deduced. Okay, and so if I zoom in on one of these, you can see that in a bit more detail, and so you can see that the computer's done a very good job in finding what the real parameters are for that. It's managed to fit the data very nicely, just automatically, and it's more a sort of robust, reliable way rather than you having to do everything by hand in all cases. If you go back to the actual notebook, you can see essentially the very last line there is what its best guess at the parameters are, and you can see that the last 3 lines it was hardly changing the values at all, so it had got to a very good model, and it can't find anything better than that. Okay, so as I say, that very last part is beyond the exercises, but please have a look at it if you want to. It's you can sort of see and maybe see how it works if you want to really go into the details. And that's the end of my coverage of the exercises, and so the best of luck, and I'll look forward to seeing your answers to those later. Right, bye bye.